Welcome to Data Skeptic Machine Intelligence, our podcast series exploring contemporary topics in artificial general intelligence and large language models. In today's interview, we're going to discuss a framework that I know in print by the initialism AIXI, which is short for, and with a slight abuse of the lettering, artificial intelligence with extra intelligence. And I learned during the interview it's also called IAXI. In any event, I don't want to take for granted that listeners know about this formalism, so I thought a little introduction would be helpful. If you're in the AI field, I think you should know about it, but if you're not, it is one of our more obscure formalisms, or at least it has been so far. Perhaps its day is coming. It's a reinforcement learning approach that leverages a concept known as Solomonov induction. Now, the key contribution of today's guest is a new idea known as weakness. It's sort of a variant idea for IAXI. The reasons why weakness are important we'll get to in the interview, but let me back up here and give you a little bit more baseline about what IAXI is. Imagine for a moment an old-timey stock ticker tape machine. I was thinking about doing sound effects, but whatever. This machine spits out zeros and ones, and that's it. Now, of course, those zeros and ones could be a binary encoded ASCII symbol. Let's break it down to the rawest terms of what data is. It's zeros and ones. And this ticker tape has a sequence of them. Now imagine as you observe this ticker tape start up for the first time and it outputs 0, followed by 1. And that pattern repeats 1,000 times over. 0, 1, 0, 1, 0, 1. Somewhere long before 1,000 iterations, you would have concluded that the machine is likely to keep outputting zeros and ones. What if the machine did 0, 0, 1, 0, 0, 1? I think after just those 6 bits, most of you would be ready to predict 0 as the most likely next digit to come out. Now, of course, that sequence could be regular for the first 100 digits, and then just start outputting random digits after that. You never know. But there's an expression I'm fond of: nature is not so cruel. So if we want a machine that can learn universally, be able to predict accurately the next of any sequence, regardless of if that sequence is stock ticker tape data, predictions about solar flares, predictions about how to win the game Tetris, or whatever it may be, a truly universal learning machine. That is really at least my take on what the goals of IAXI are. It embodies the concept of Occam's razor, that the simplest solution is likely the correct one. IAXI, at least in theory here, this is how it works on paper, could be thought of as a probability distribution over every possible Turing machine. That is to say, every computer program that could be outputting those zeros and ones. The simplest programs are the shortest ones, and those do seem to be the most likely in a lot of cases. Like I said, nature is not so cruel. You want to find a model that is not overly complex, but not so under-complex that it can't describe the world. There's one elephant in the room when you talk about a theory like this. If it's considering the probability distribution over all possible Turing machines, well then due to the halting problem, we can never fully compute its solution. So what good is IAXI? Well, at a minimum, it's a theoretical benchmark. We can study its properties and talk about it from an abstract mathematical point of view. In this sort of theoretical, uncomputable version, there are probably interesting things to be learned, albeit on the theory side. However, it doesn't end there. There are interesting ways you could explore how approximal versions of it could work out. Maybe it considers only the Turing machines that halt within a certain amount of instructions, or some limited system like that. Maybe there's a way it can be epsilon close to the optimal solution but computed in efficient time. Maybe there's a deep learning plugin that could approximate some aspect of this and learn the belief update step. I don't know if any of those are good ideas or not, but one idea that does sound really good is this weakness idea. With ideas like this, the IAXI framework might become practical. While it's sometimes hard for my imagination to stretch from the pattern of 010101 being learned quickly to imagining a system that could learn when streaming video data is passed through it in the same fashion. Sure, it works in theory. Can we scale that up in practice?
My name is Michael Timothy Bennett. I'm a Ph.D. student with the Australian National University. I'm studying artificial general intelligence, or more specifically, mathematical formalisms of artificial general intelligence.
So there's a lot of mathematical approaches, Bayesian approaches, supervised learning, reinforcement learning. Do you have a specific focus within that tapestry?
I guess it would have started with a Bayesian approach because Marcus Hutter, who came up with IAXI, was at the ANU, and I was, learning about his theories because he was there. And how his theory is called IAXI. It's a formalism of a Bayes optimal agent, and I started from there and trying to work out why is first of all IAXI incomputable and what can be done about that, and also one of Hutter's students, Jan, when I think he was, I don't remember if he was there when I first came to the ANU, but he was working on why IAXI had subjective performance. So one of his results from his PhD was to show that IAXI was only optimal if the Turing machine it was using was the same as the Turing machine that Leadcutter intelligence was sort of being measured with. So essentially, it's like thinking the Turing machine I think the world is running on is kind of like the Turing machine the world is actually running on. So that made everything sort of subjective.
Well, interesting, because most of the time when you encounter a Turing machine, we're making arguments of universality and how it doesn't matter what shape or size of Turing machine you've got, or how many read heads it has, or whatever. What makes a difference here?
I mean, the way I try and explain it in, I suppose, a much less formal way than Jan would in his
Sure, yeah, yeah.
paper, is if we have three functions. You could think of it as function one is the mind, function two is like the body, and function three is the environment that's sort of determining what intelligent behavior looks like. We can find the optimal function one for the environment, but then if we compose these functions, you've got function one inside function two inside function three. If you change function two, it doesn't matter how good your choice of function one is. You can always change function two to sort of ruin the day of function one, so that the performance looks terrible with respect to the environment you're in. Of course, that's not exactly how IXE works, but it does convey the gist of the problem in a way I thought was helpful because I was trying to talk to philosophers as well as mathematicians.
Well, if I pull out my Russell and Norvig textbook on AI, their agent model is the agent and the environment, and arrows going both directions, sort of a two-layer system. You
Mm.
described it as like a more of a three-layer system. Why do we need the extra layer?
In Russell and Norvig's the Asian environment paradigm, it's you've got actions and percepts, and they're sort of going around. But what those actions and percepts are is sort of assumed to be given, right? So I start with the idea of I know how to grasp things. I have an arm. I have objects I can recognize in the world. When we're building robots and things, of course we can do that. We can train a neural network to recognize cats and then say, look, here's a cat, and that's all well and good. But if you're trying to make something that's optimally intelligent, the type of abstractions you give it are kind of part of that intelligence. What if what matters is not recognize arm or leg, but recognize a sort of the body the arm or leg is attached to, and you've only given it the abstract representation of an arm or a leg? So you want to recognize that there's a whole object composed of two abstract objects. Unless the thing can learn abstractions on its own, it's not really going to be able to reason about that information. Like the Turing machine, and or sort of in the agent environment paradigm, we're assuming certain interpretations are given. The point of the formalism I was working on was trying to work out how we could have it so that there was no interpreter between the sort of mind and the world the mind is pursuing goals in. So there's a really trippy idea in cognitive science called inactivism. Instead of conceiving of cognition as sort of separate from the environment, something you apply to the environment, it's just part of it. So, for example, under this sort of paradigm, we'd think of cognition as extending into the environment. If I'm trying to compute the solution to a math problem, I can use a pen and paper in the environment, and so my mind is extending into it. I'm performing computations there, and then the environment, the resources in it are part of my cognitive process, which is, I suppose, intuitively obvious in that example, but it becomes a little weirder when you think of it in terms of I'm trying to plan my day, and then say I've got a nutritional deficit and that's hindering my ability to compute things. In order to represent that, I kind of had to just represent a task, and the task is the mind and the environment in which is being pursued. So it was a very different model.
Well, there's various forms and milestones in artificial intelligence have come to the public's attention, we start to know what they're for, right? People know Stable Diffusion is a image generator, ChatGPT is a conversational agent, Alpha Zero plays a large class of different games. What is and sorry, I know Marcus Hutter's model from writing only, so to me it's AIXI. I'm going to try and say it your way. AXI, is that right?
IXI. Oh yeah, yeah,
AXI.
IXIs, right. I don't know. I just call it IXI. I actually don't know what he'd prefer to call it.
Well, we'll do both
Never.
then. Where does IAXI fall in that pantheon? How can we summarize what it's for?
Given a definition of intelligence, what would an agent that maximized that definition of intelligence look like? And how would it behave? So it's really useful understanding how, if we had a theoretical superintelligence, what it might do in terms of how its relationship to humans. So it's used in AI safety research and things like that. It's also a demonstration of how we might apply compression to come up with something that makes better judgments about the world. So IXE selects the simplest, it prefers the simplest model it can identify that explains what it's seen. So it measures simplicity in terms of Kolmogorov complexity as part of this process called Solomonoff induction. And that's basically a formalization of Occam's razor. You know, the simpler hypothesis, simpler explanation is more likely. We don't know why simpler might be better, but it does tend to be. And Marcus took this Solomonoff induction and applied it to an interactive setting with a reinforcement learning agent. That was a really sort of novel combination of ideas. While it's incomputable because Kolmogorov complexity is incomputable because we can't know what the smallest possible lossless representation of some data is, but it certainly is a really interesting model. I mean, it inspired my entire PhD. I didn't even plan to do a PhD, and I started learning about this thing, and I became fascinated with it, and then started learning about all this philosophy of mind, and tried to combine disparate ideas, you know, largely inspired by that.
Well, the motivation you described that the simplest model probably has the is the correct one or seems to have a good explanatory power. But if I take that to a perverse extreme, maybe I would adopt the philosophy that the universe is totally random. I can't control anything. It's a flip of the coin at all moments, and I'm just experiencing whatever happens next. That's a pretty simple to describe model and to compute. It's probably not the one I actually will pick. Why not?
Yeah, yeah, yeah. So it is based on this assumption that you've got a computable environment. It's a pretty reasonable assumption, right? The world seems to be computable. I mean, we keep coming up with mathematical descriptions of relationships between things, and they seem consistent, or at least locally consistent. Maybe if we moved to another solar system and have different laws and everything, it'd be weird. I don't know. Just crazy
Well,
shit.
nature doesn't seem to lag in my experience, so
Yeah,
nature seems to be computing reality, if nothing else.
yeah, and so that's very much the assumption I started all my. There's an idea called pan-computationalism, that you know everything is a computational system, and I sort of I threw out the simplicity thing for my research, but pan-computationalism was the basis of everything, and yeah, I don't know what we could do with any scientific pursuit if we didn't make this basic assumption that things are got a consistent computable relationship.
One thing I'd like us to zoom in on that we've touched on, but I think would be illustrative for listeners, is this notion of computable and uncomputable. What about IAXI is uncomputable, and why is that a problem?
If I want to find the say I have a whole lot of data and I want to find a smaller representation of it. So I want to find a way to represent, say, the numbers from, you know, 0 to 1,000, and they're all integers. That's a compressed representation of those numbers. What I just said was compressed representation because I could, you know, explain this process by which we could generate it. We take all the numbers from 0 to 1,000, and it's only the integers. We eliminate everything else. So that's a lossless representation. Now, I can keep looking for shorter and shorter lossless representations of some set of data, whether it's numbers from 1 to 1,000 or something much more complex, say the history of all my interactions with the world in IX's case. The reason it's impossible to work out what the smallest possible representation might be is just because if I'm trying to compute programs that regenerate this data that I'm trying to compress losslessly. So I come up with a program and I run it. I see if it regenerates the data. That could just run forever. So that comes back to the halting problem. I can't guarantee. I mean, I could sort of stop at some point, but then I don't know. Maybe it would have eventually reproduced the data. Maybe it was the right program, and I just killed my chance to find the optimal program. There's no way around that. So that's why it's an insurmountable problem. But it is approximable because I can stop things. I can sample programs of ever shorter length, and so there are versions of IXE we can approximate to an arbitrary degree and and experiment with.
Well, in its uncomputable definition, I guess you're kind of saying we have a probability distribution over every possible Turing machine as our hypothesis of how the world works. If the universe truly is computable, I think we agree, then somewhere in that distribution is the correct answer, is the right model. It's just zoning in on which one of all those Turing machines it is. But as you point out, we're never going to find the exact one. That's impossible for the halting problem and reasons like that. So maybe we can get epsilon close to it or something like that. But do we miss something when we know we don't have a guarantee of finding the optimal one? Does the approach lose all its luster because of that?
Um, I don't think it loses its luster. I think it. Well, this is one of the things that I was trying to get out of my research. It's like
Hmm.
what really would be the most likely explanation of things? I mean, is it going to be the simplest? Clearly, humans can come up with pretty good explanations of things. We don't necessarily go to the optimal thing, but we are right very often, and at the very least, we have an interpretation of things which is consistent with other humans. Otherwise, we'd struggle to predict, particularly other humans, and they're arguably one of the most dangerous things in our environment. It's one of the things that's most important for us to get right. That's also one of the things that made me think, well, it's not so much about optimal choices of model given the environment, but optimal choices of model given other humans. And our own biology is sort of it's information about what other humans might do. Our own feelings inform the choices we make. Our reactions to events inform the choices we make, and then those inform our preferences, what choices we make. So if we want to predict other humans, it's not necessarily the optimal model of the world that we're going to go for, but what would I do if I were in that situation? And so that's additional information we can use that in the case of IXE is not necessarily present. But this also gives us all these biases in our decision making, that sort of holes in that where we frequently make mistakes. A famous example of the result of some cognitive bias was the O-rings in the Challenger. There's a space shuttle that blew up in the 80s where they said, okay, we've got two O-rings and they're not both going to fail. Except that's exactly what happened, because if the cold conditions that cause one of them to fail also cause the other one, cause them both to fail. So same failure, single point of failure for both redundant measures. And it's just the way that we tend to think about the world is to simplify things along certain lines in order to predict what we need to rather than what is optimal.
So if we want a practical, usable version, we have to have not the kind of theoretical axis that computes that is uncomputable. We'd like some computable version of it. What limits can we impose that get us there?
I mean, rather than IXE, right? So I'm going back to my own research here again.
Yeah.
And so instead of simplicity, I'm using this thing called weakness. And so I've got this proof that weakness is optimal. But if I'm trying to predict language, so I've got the paper on, it's one of the ones, the one on meaning that I sent. If we're trying to compute what someone means rather than just what they're saying, I can't just use this, what's the weakest hypothesis? I've got my own information about what they might say, which is my own preferences. So I take the set of choices which would explain the behavior I'm seeing based on my own preferences, and then search for the weakest hypothesis within that. So something that contradicts the fewest number of possibilities.
Could you contrast maybe the motivation for developing weakness? We've got the idea of simplicity that has pros and cons. What motivated your exploration for something else?
Well, I was reading. I was thinking about the probability of generalization. In the case of IXE, the definition of intelligence it uses is the ability to satisfy goals in a wide range of environments. But that's not necessarily the most compelling definition of intelligence I'd heard. And And so I was thinking about, generalization, this G factor from some psychology and things from decades ago. And then during my PhD, a guy named Francois Chalette at Google published a paper arguing that, yeah, intelligence should be the ability to generalize. He presented a whole lot of arguments. And so that saved me a lot of work in my PhD now, because I can just cite that and say, look, here's an argument as to why generalization is a better definition. Effectively, if you can generalize and you make a couple of extra assumptions about your ability to actually represent these goals and learn them, then in order to achieve goals in a wide range of environments, you're going to need to be able to generalize, because you need to learn efficiently. It's how fast you can learn, how little information you need to do it. And also, generalization is going to imply your ability to satisfy goals with some extra assumptions. But if we do that, then why not just measure the ability to generalize directly instead of looking at, say, the length of the hypothesis? And you can do that if you've got, say, if you're a computer with a finite number of bits or something like that. You can compute the number of possibilities that, number of permutations of bits you can represent. And so if we make the assumption, the quite reasonable assumption, that we're going to have a finite number of things we can reason about, then you can compute the likelihood of generalization given a hypothesis. And that's what weakness is. And then you can compare that to description length. Instead of Kolmogorov complexity, where it's like we've got a language we've written our hypothesis in, and then there's sort of, you can think of it as another language the world's operating in. It's like, and we've got this Turing machine translating between, so we can come up with a more compressed representation. Minimum description length is like everything's written in the same language. So I've got something that's, say, a length 5, and I can see whether or not that explains some sequence of propositions. And this is commonly used in, say, inductive logic programming, which is, I've got a sequence of events which have happened, and I'm trying to come up with a hypothesis that explains them perfectly. So a similar kind of problem. And weakness massively outperformed description length in the experiments to learn. I was specifically having it learn binary arithmetic and multiplication. It seemed like an appropriate choice of thing to experiment with, because a lot of machine learning struggles with that. And so when I say it outperformed, what I mean is there were fewer examples required for the weakest hypothesis to arrive at the correct relationship between bits than it was with minimum description length as the heuristic.
Are you able to inspect the hypothesis? Can you look at it and say, sure enough, that is the operator, that is the algorithm for binary multiplication or whatever your true goal state is?
Yeah, you can. We're talking very small number of bits here. I mean, this was like 8-bit strings, so it's very simple, like just logic. And so it was not particularly, I mean, if you could have brute forced it with that number of bits without too much trouble. So it was a very controlled scenario. You can see, I showed it to, Marcus has a reading group every couple of weeks. It still runs. I've been remiss in my attendance lately, but I presented this, and the one thing he said was, I want to see how it scales. So I have to build a more efficient program and then see how it scales. Because,
Gotcha.
right, my initial implementation is really slow.
Do you find that that's an implementation thing, or is it like an algorithmic big O kind of limitation?
Oh, I mean, it's like Boolean satisfaction problems are sort of, I think, NP hard and all of that. And it's so that, yeah, it's a difficult problem, but they're really efficient solvers for this stuff. No, the reason this is slow is because I used loops in Python, and Python hates loops. It really hates loops. So I'm gonna have to rewrite it in Rust. I think.
Yeah, I bet you'll see a good performance boom with that.
Yeah.
Can we talk a little bit about some of the formal results? What does switching to the weakness approach give us that we can prove?
So there's two papers sort of published alongside this weakness paper, and they're all at the AGI conference. So one of the papers deals with the sort of construction of identities for objects, and the other one deals with language. So the first one is probably the more interesting, because if I am trying to come up with weak hypotheses about the world, and I have a sort of a task that is the product of all the feelings I experience, the heuristics, the things I'm compelled by. So the reason I don't just sit at home, my reward signal sort of specifies a task. That task has a whole lot of subtasks, and I can take every decision I make and sort of take every combination of decisions and form a task description out of that. Each of those has a set of hypotheses associated with it. Each of those hypotheses or models can be used to reconstruct those decisions, construct a rationale or intent that would have motivated those decisions. If all of these models are kind of the intent or goal of my decisions, then if I'm trying to predict something in the world and I know that my performance is optimal, then for me to have optimal performance, I should have a representation of that object's intent as well, what it's going to do, a prediction. Then that would be a sort of a part of the model that I have. That's kind of a representation of that object's identity and its intent. From there I can abduct what it's going to do because it'll be a weak representation. So assuming I have the tools to represent that in my computational language, I'm going to be able to simulate what objects in the world are going to do, like other animals or even walls and doors and how they're going to react. And so I ascribe intent to all of these things and construct an identity for all of these things, anything that's going to impact my goals. So it's not like I'm constructing an identity for everything in the world. It's just the stuff that meaningfully affects my ability to complete the tasks I'm trying to complete. This just comes back to what I was saying at the beginning of the discussion, where I was saying that we need to the abstractions we form are part of the cognitive process. If we choose to form one abstraction and not another, that's a really important decision for our performance in the world and then how well we're going to be able to satisfy our goals. So we construct identities for these things that meaningfully affect us, and some of those are going to be other people, but also ourselves for our own actions. And this comes down to causality. There's a field of sort of causal inference, and there's a whole lot of interesting results from that showing that is about a deep mind that's showing that if I have an autoregressive model, like say one of these language models, and I want it to reason correctly about the world, I need to distinguish between its own interventions in the world and it observing the same set of events in the world, but without having intervened to cause them. It needs to be able to tell whether it's caused something in order to perform well. And this is intuitively obvious when you think about it from a human point of view, right? I need to know that I was the one that caused the market crash if I'm going to take advantage of that information in future or something like that. And so this sort of explains how we construct and represent our own identities and have a sense of self-awareness, which is it's a trippy idea. So obviously it's got some interesting reactions on the internet, but it's published research now.
Well, if I understand your definition of weakness correctly, it's defined with respect to tasks and the tasks an agent finds himself capable of completing. Is that right?
Yeah. So the idea is that your mind is part of the world, and so rather than applying that mind to the world, we just have a task which specifies everything you're trying to achieve, your goals, together with your model of the world. It's kind of combining them together. There's this Heideggerian idea of Dacian a little bit, although philosophers will get angry at me for using that.
Do you put a lot of thought into defining the tasks? Like, let's say it was a mathematical challenge. Asking an agent to learn to multiply two numbers is a feat. Asking it to factorize numbers a little harder. Asking it to output a proof that p does not equal np, even much more harder. How do we decide what are appropriate tasks?
Well, I guess the way I was thinking about a task is just it's something that's specified by my very existence. So the fact that I have a particular body with certain urges I need to satisfy, it implies a task. So it's just a way of thinking about combination of, say, if I were to take the traditional sort of reinforcement learning model, things like I have a policy, but I also have like a reward function, things like that, and I'm just combining all this stuff together into a single sort of object called the task. But if we're to do this from a practical point of view, like actually implement this in something, I guess we try and actually specify, like you were saying, like multiplying numbers together or something like that. Something we've already come up with, which is a lot more complicated than just saying, oh, robot has feelings, the end,
Yeah,
and letting it run around in the world.
yeah.
It's a difficult problem.
We touched a little bit earlier on the experiments you ran, but I'd love to go a little deeper there. Could you refresh listeners' memories about what kind of experiments you were conducting?
Set of it's an 8-bit string prediction problem, where I have a set of 8-bit strings. Each of them represents a particular instance of an operation. So the two operations I used were binary addition and binary multiplication. So you have a few bits that would be input, a few bits that would be output. And I want the computer to learn this relationship between the bits, but I don't tell it this relationship between the bits. Instead, what I do is I take these sets of bits and I pick one of the bits at random, just any one of them. It doesn't matter which one. I delete it from my examples, and then I take, say, two of the 8-bit strings, and I say, can you tell me, based on these two 8-bit strings, what the eighth bit is going to be? And usually it'll sort of with two examples out of the possible 16. And more often than not, it'll be wrong, right? It depends which two examples I give it, but it's going to tend to be wrong. Now, it might just be that this bit is always just tends to be one or something. It's a bit random. So I keep iterating, trying different combinations of 8-bit strings and see what the average performance is over many, many iterations. I take, say, 4 examples and see, is it getting it right? And I do this using both the weakest possible hypothesis I can construct from these 4 examples and the minimum description length hypothesis I can construct. And I find those using a variation on A star, which is
Hmm.
search algorithm. And I just keep increasing the number of examples and compare the performance of description length to weakness. And so, eventually they're both getting it right most of the time with enough examples. But yeah, you can see that particularly at the lower number of examples, weakness was outperforming.
That sounds like an advantage that it's going to perform better, that we'd want to switch over from minimum description length to weakness. Could it be, though, that it's too ambitious or overly confident or something along those lines?
Yeah, it's a surprising result. I mean, I haven't found a fault with it yet, and nobody else has either. But it's not to say someone won't. So I mean, I decided to call the thing because it's a deviation from the idea of simplicity. I called it Bennett's razor, and if someone finds a fault with it, I'm going to rename it Bennett's folly. Um, which,
Sounds good.
yeah.
Um,
And I suppose calling it Bennett's razor is a good incentive for someone to try and find a problem with this. uh, yeah.
well, I'd love to see larger and scaled up experiments of it continue, but in lieu of those in the moment, do you have any hypothesis about the asymptotic properties as you scale this up? How will this approach versus like the MDL approach pan out?
I mean, if we're able to learn from less data, we're able to have an agent that adapts much quicker. I mean, it seems like it's good at identifying, at least given the simple examples I've used, it seems to be good at finding the actual true underlying processes. Like that we are, it maybe this is, it does tend to be that weaker hypotheses really are, the most likely to be true. And so we'll just end up with far more accurate machine learning. Also, it'll be good for, say, one class classification and anomaly detection. In all these experiments, I was only using positive examples. Like you can learn more efficiently if you have positive and negative examples, but it's a harder problem to just learn from positive examples. And that has all kinds of applications in things like a fault detection in aircraft landing gear, to detecting intrusions on networks. Obviously, you'd need a much more scaled up version to help with that. But if we can integrate this with the, say, existing approaches to, right now, it's just something I'm using with like perfect sort of logical representations of stuff. But if we can integrate it with, you know, transformers and the function approximation techniques from machine learning, we could just make way more efficient, cheaper machine learning. We could make models that learn from the minimum number of examples possible, which would mean that instead of having to get data centers with thousands of GPUs and millions of dollars to train a model, I could train a model on my laptop. I mean, it'd destroy a lot of startups that have just been built, I'm sure. But hey, it'd be a nice. It'd be scary as well. Like the ability to construct accurate model. I mean, all this stuff's a bit scary. That it's fun too.
Well, work like yours has a great deal of theoretical value, helps with the thought share on what AGI will be or how we rationalize about it and think about it. But there's also a hint of practical use cases beyond the 8-bit predictions you were mentioning and that we just kind of touched on. What do you think are the near-term industrial or practical possibilities?
I'm planning to exploit those. So I might leave that one alone and
Sure.
just try and do it. Yeah. That's my post PhD employment plan, actually. Um, once, we'll see how it pans out. If I'm working as a postdoc in a couple of years, you know what happened. Um, yeah.
Michael, where's a good place for listeners to go online to learn more about your work?
Aside from official journals and things, I got a website, michaeltimothybennett.com. I have a Twitter where I'm constantly tweeting things. I mean, there's a lot of stuff about my work on there. That's MITIBENNETT. That's the handle, Mighty Bennett. I mean, it's remarkably hard to get Michael Bennett as an email address or a handle.
I'll bet.
So,
We'll have links to those
yeah.
in the show notes for listeners to follow up. Michael, thank you so much for taking the time to come on and share your work.
Oh, thanks for having me on, Carl.